In this lecture, we're going to expand what we saw in the last lecture about Laplace transform. And we're going to try to understand what exactly the Laplace transform does. In the last lecture, I just presented the Laplace transform to you with some fancy equations. Well, that's very nice. We can convert equations, differential equations, into functions of s and do the opposite, and solve for differential equations that way. But how exactly does that work is also very important. So that's the focus today. We'll see what exactly we are doing when you take the Laplace transform of a signal and hopefully make some meaning of those fancy equations, which will hopefully help you understand the concept a bit better, and then do a few exercises. Depending on how this lecture goes, we can have another lecture on Monday just to do exercises on Laplace transform and perhaps some convolution. Or if you feel like you are comfortable with Laplace transforms, we can just move on. So let's assess that at the end of the lecture. Type on the chat as I go if you have any. If you would like to see more examples of Laplace transform in the next lecture, or if you can move on. So this is a bit abstract you're going to present. I'm going to try to make sense of it, but it's not very hard, very easy to grasp. So if you have any questions, if you need me to repeat anything, please interrupt me and ask questions. Questions are welcome at any time. Just interrupt me, and if anything is not clear, that's my fault. So just interrupt me and ask me to repeat as many times as you need. Okay, there are no stupid questions, there are just valid questions. All right, so let's get started. Today we're going to expand what we started in the last lecture, review the principles of Laplace transform, try to create a graphical representation for the Laplace transform, and see exactly how that can be used to solve for differential equations. So what is the process? What is happening when you take the Laplace transform of something? And then apply the Laplace transform to a mechanical system. We'll do another example in this lecture, right? So let's go back to lecture 5. We saw this there, just a quick reminder here. What exactly is the Laplace transform? Well, the Laplace transform is a way to convert differential equations that are written in the time domain into a new domain that we call the frequency domain, or the Laplace domain, where the differential equations will now be replaced with functions of s. And this s is what we call the Laplace variable, which has some important meaning behind that symbol of s. We'll see what exactly that is. And once we have that a new formulation, we can now combine terms and manipulate equations better, because all the integration, the derivation, that's gone. We have now functions of s. It's a lot easier to calculate that way. And then you can go back to the time domain by taking the inverse Laplace transform. So the process will always take 3 steps. The first step is to obtain these differential equations, then take the Laplace transform, convert them into the frequency domain, solve for the variable of interest, and then do the inverse Laplace to go back to time domain. And in the process of going back to the time domain, we basically solve the original differential equation. Okay, so what exactly is happening when you take the Laplace transform? Well, the idea we'll see is relatively simple. Let's consider here this mass spring system. If you write the equation for the mass spring system, we get equation 1, mass times acceleration plus the spring force equals to the output or the input force to the system. That's the balance of forces acting on that mass spring damper system. So this is a second order differential equation. We have mx double dot plus kx equals to f of t. And now if you want to find the behavior of this system, assuming that x is the displacement, we want to solve for the displacement, we need to solve for the second order equation. But we know that when we deal with differential equations and any physical system that is derived, that is modeled through such set of differential equations, we only have 2 possible solutions. The solutions to equation 1 are either exponential or sinusoidal. They can never be anything else. So why? Because if you take the derivative of an exponential waveform, you will still have an exponential waveform. It's scaled, but it's still in the shape of an exponential waveform. It can only be sinusoidal because if you take the derivative of a sinusoidal waveform, you get a sinusoidal waveform that is now shifted over time and is scaled, but is still in the same shape. So these are the two mathematical operations that do not change shape when you take the derivative of them. And that gives us a very good understanding why these are the only possible solutions to the differential equation. The third option is that we have a combination of them, a combination of sinusoidal and exponential, and you will take the derivative, same thing happens. So if you want now, if you know that the solutions to equation 1 are only exponential or sinusoidal, we can create potential signals that could be used to solve this differential equation. So if the solution is only exponential, then you can write a tentative expression for x of t as follows: exponential of negative sigma t. If sigma is a real number, then that gives an exponential that either decreases if sigma is greater than 0, or increases over time if sigma is smaller than 0. So this gives simply an exponential function. If we write in the other way, if you want to create a sinusoidal waveform, we can use Euler's theorem, since this would be better written as follows: plus j cosine of omega t. Now, if you have a sinusoidal waveform of magnitude omega, we could write that in the form of exponential of negative j omega t, where j is a complex variable and omega is the frequency of that signal. If you expand the exponential of negative j omega t, that is equal to sine omega t plus j cosine of omega t. So two options. So if we have an exponential with a real number that gives an exponential, if you have an exponential to a complex variable, that will give us a sinusoidal waveform, purely exponential or purely sinusoidal. But we could also take these two signals and combine them. And that's the third option. Now the signal we are creating, that is potentially a solution to equation 1, is a signal that is both exponential and sinusoidal. How do we make that? Well, we simply multiply both the sinusoidal and the exponential here. And when you multiply them, we can simply add the powers of the exponential there, and you have exponential of negative j omega plus sigma t, or exponential of negative st, where s is sigma plus j omega. We see our famous s here, the Laplace variable, that now has a real part and has a sinusoidal part. Sigma is the real part, j omega are the complex part, omega is the frequency of the signal, the exponential, the sinusoidal component of that signal. Now we could potentially use this formulation to change omega and change sigma, and then try out in equation 1, see if they work, see if that solves equation 1 for all values of sigma and omega. That would take quite a lot of time, and that's where the Laplace transform will come in. Is a way to find what sigma we need and what omega we need in order to create the solution to the differential equation, which will then give us the signal of interest, in this case here x of t, that it could be that one, for example. Okay, so here is the formulation of the Laplace transform. This very fancy equation here, but what exactly are we doing? Well, inside here we have exponential of negative st, where again s is sigma plus j omega. And Laplace realized that if the solutions can only be exponential and sinusoidal, all we need to do to find those points, to find sigma and omega that will make up for the solution of the equation and give the signal x of t, is to create random signals, compare that signal with the original signal we have that would solve the equation. And that way we can find sigma and omega and represent that in a new domain that now, instead of time, is the frequency and omega and sigma domain, the S domain. Okay. So let's apply that to an example and see if we can make more sense of it. I'm going to use the light board for this, but you have these 3 slides here. I'm going to use the light board for that. Yeah, but you can follow that on the next 3 slides. Okay, so let me just click on outside. There you go. All right, so let's assume that we have the signal x of t, and we want to find what that signal is. This signal is the signal that we got as the solution of a differential equation, or the signal that represents, for example, the displacement of the mass in that mass spring system. Well, this wouldn't be because we need some damper, but assuming that this could be the solution to the differential equation that describes the behavior of that mass spring system. We want to recreate this signal, and to do that, we can use the idea of the Laplace transform, because you know that this signal can only be exponential, it can only be sinusoidal, or it could be a combination of them. Which is exponential of negative sigma plus j omega t, which in this is s. So the question now is, if you want to recreate this signal, what is sigma? What is omega that we need to input here to create a new signal that actually matches that signal exactly? Well, the signals that we can create through this formulation now can range from all the signals we see in this graph here. If, for example, we take this signal, here would correspond to omega equals to 0 and sigma greater than 0. Sigma greater than 0 will make this exponential here decay to 0 as time goes to infinity. So this is time, and this is the magnitude of that exponential. Is this signal here, down here, is the same, is omega 0, and sigma in this case is also greater than 0, just going in the opposite direction. Or we could have an exponential that grows to infinity when sigma is smaller than 0. We could have a purely sinusoidal waveform. If you take this signal, for example, in this signal here, sigma is 0, and omega is greater than 0. That is a purely sinusoidal waveform. Exponential of 0 is 1, so you are left with that. And you can also see the red signal here. You see that the red signal is interesting because the red signal is a sinusoidal waveform that decays over time. And what is making that a decay is that is bounded by these two exponentials. So this signal has sigma greater than 0 and omega greater than 0. Right? None of them are 0. In this case, we created this sinusoidal waveform that decays over time. The question still remains, well, we have the ability to create any of these signals or a linear combination of them. And the question is, what is sigma, what is omega that will make up for that exactly signal we see there? So to do that, we'll need a way to first create these random signals. Second, compare with that and evaluate how close they are. And if they match, then we found sigma and omega that will give the signal of interest. Okay, any questions so far? Any questions? No? Okay. So if there are no questions, I'm going to move on. Right? So if I don't hear anything, I'll just keep going. But if you have questions, please interrupt me. Okay, now we need a way to somehow make up these random signals and compare them. So let's see what we can do here. So here I have this 3D plot where the bottom here, the bottom plane is simply a 2D plane with one axis having sigma, the other axis having omega. So if I pick a point here, this point, for example, gives me that value of omega and this value of sigma. So I could, by using this point, create any signal that I want by picking this sigma and this omega. Okay, so now let's assume that at this point here and that point, because this is a complex axis, so meaning that if a point exists here, it will exist on the other side. Complex numbers, as far as this course is concerned, is always coming in conjugate numbers in pairs. So if we have a positive omega, we have a negative omega. Let's assume that this point or that point are the exact combinations of sigma and omega that we'll need to create a signal that will match x of t. So if I take a new signal, let's call this signal a probing signal, let's call this xa, which is the exponential of negative sigma a plus omega aj times t. If I take omega a from here and omega a from here and sigma a from here, make t go to infinity or whatever, and I look at the signal I create, let's assume that we got lucky with our selection, and this is precisely what matches the signal we are considering. So if we know that the red dot is the exact point we need, the exact omega and sigma, what happens if you take this point instead? Well, if you take this point here instead, we have the same frequency, but we have a smaller sigma. We have the same frequency, but a smaller sigma, meaning that the signal we see here, we create through that point, will decay slower than the actual signal we are trying to recreate, which is taken from this point here. Because the sigma is smaller, we have exponential of sigma t. The smaller t, the more time it takes to decay. So if you take that signal by accident over there, we should see something here that decays is lower. It will have the same frequency, but it will decay slower. Yeah? Okay, so these two signals don't really match. How do we know that they don't really match? Well, that's where this fancy integration comes in. This integral is nothing else than just a way to compare how close the signals are. So we are taking here is the signal, original signal we are trying to create. We multiply that by the signal we just made up using that point of sigma and omega. And you're going to multiply them and take the integral. So what does that do? Well, let's first multiply them. So if you multiply them, we see that up to this point is positive. Positive, we have a positive number. I don't know, somewhere around here. From this point to that point, we'll have a positive times a negative signal. Positive times a negative signal will have a negative number. So it's going to come down like that. It's going to stay. Now here is negative, negative. The signal jumps to positive, and so on. It will have portions where it is positive when they are the same sign, like here and here. And they will have negative signs. The multiplication will be negative when they don't have the same sign. And then we create this multiplication of these two signals, which is now the multiplication inside this integration here. And now we take the integral of that multiplication. What does it mean to take the integral of this curve? What are we doing? Aren't we just taking the area, this area, minus that area, plus that area, minus this area, plus that area, and so on? So the integral is the sum of all these areas, and is now the third dimension of our axis, is the result of this. I can take now this point and give the magnitude here and here, of course, because they are the same. Right? And this point is now the magnitude of the multiplication and the integration for this combination of sigma and omega. Any questions? Any questions so far? No? Okay. Again, if you have questions, just ask. So we picked a random point here, created a random signal. We multiplied the signal with our original signal. Here is the multiplication. We took the integral, and the integral now, because these signals don't match, we see portions of the multiplication that are positive, portions that are negative. So when you take the integral, we are taking the net area here. But because they never match, there are positive and negative components. The result of the integrations is a finite number. It's a finite number, and there this is the result of that. Okay. Now let's move on, and let's assume that we got the other point instead, which would be this point here. What happens if you pick this point instead? Will data decay is lower or faster than the actual signal, or will that match the signal in any way? What do you think? If you take this point now, we see that we have the same frequency as the signal, because we know somehow that this is actually the point we need, but we by accidentally took that point. So we have the same signal, the same frequency as our solution, but we have a greater sigma. If sigma is greater, exponential of omega t will decay faster than the actual signal. So the signal will disappear faster. Again, we can now take the signal we created through this point here. That's exponential of negative st. S is sigma plus omega t. That's the signal. We multiply them. So same story again. Portions of this multiplication are positive. Portions of this multiplication are negative, and so on. And you take the integral, is this plus that, and so on. So because there are negative portions, we'll have the same effect. The result of this operation will be a finite number of no particular interest. This is the magnitude of that operation. Now, and these points are boring points in the space. They don't really tell us anything, because what they are telling is these are finite numbers. And because they are finite numbers, we got negative portions in the integration here, meaning that at some point, the signals that we made don't match. Now let's take the correct point that would create the signal. What happens? Well, when we find the actual point, which in this case is the red point here, this is exactly the frequency and sigma that we need to make signal x of t. So the signal we are going to make using that is exactly the same. And so on. What happens when you multiply these two signals? Original signal I created. What happens when you multiply them? Do we have any negative portions in this multiplication now?
It's all positive?
It's all positive. Aha, it's all positive. If the signals are the same, it's the same as taking x squared. And the square of something is always positive. So when I multiply these two signals now, I always have a positive area. Aha, when I take the integral now, it's this entire area, which means that here it will show as the highest possible value in the magnitude of this operation, which is x of s. It will reach its maximum value when the two signals match perfectly. And bingo, that's exactly what we wanted. Now we know which point in this integration, in this plane, which combination of sigma and omega are required to make up this signal, because when the multiplication reaches its peak, that's the signal we made. So then let me try now to make this a bit somehow easy to understand. So these 2 points will tend to infinity. They will not be infinity, they're going to be a very large finite number, but they will be the highest possible number we can get through that. And you can now populate this entire plane by simply changing sigma and omega, and you can create an entire map, a three-dimensional map, and the peaks here will indicate the correct points that will make up for that signal. All we need to do now is to watch this map and see where these peaks occur, and then we know that the signal we are looking for. This map is populated through one step in this integration. When you take the integral is for all values of s, meaning that we take this entire plane in one go, input that in the integral, create these magnitudes, and try to approach signal x of t. Now, we are not quite done yet, because what do we do with that? Well, we'll see. But there's another interesting point of interest here. So all these points that don't go to infinity, they are boring points. They don't carry any particular meaning, and they are just there to tell us that it's not the right combination of sigma and omega. But there is one particular point that it could be interesting, is where this function tends to 0. Here in my drawing, that point doesn't exist, but let's assume that for a certain point, let's say point 0 here, these graph tend to 0. It will be 0. The magnitude, the sum here was 0. In this particular case, I chose sigma to be 0, omega to be 0. That gives exponential of 0, excuse me, exponential of 0, which is 1. So exponential of 0 is 1. Right? By choosing this point here, omega 0, sigma 0, exponential of 0 is 1. So I'm now taking simply the integral of the signal x of t, because this exponential of negative st is 1. What happens when I take the integral of this particular signal? Well, I'm adding this area to that area, to that area, to that area, to that area, and so on. And that's 0. That's going to give us 0, because it's symmetric. It doesn't happen for all signals, and doesn't have to. For this particular signal, if we choose omega and sigma to be 0, we just take the net curve, the net amount of area here, and that turns out to be 0. So that's another point of interest, that brought this function to 0. So those are all the points we care about. Points where the integration blows up to infinity because we are now approaching the correct value of sigma and omega to make up for x, and points where this goes to 0. And what can we do now? Well, now we can take this graph and only focus on these points of interest and try to create a function that is now a function of s, a function of sigma and omega. Remember again that s equals to sigma plus j omega. We create a new function of s that when this function approaches this point, it goes to 0. When that function approaches these 2 points, it goes to infinity. We'll do that in the next slide. But before we get there, are there any questions here? Any questions? It's very hard to gauge how slow or fast I can go here if you don't give me any feedback. No questions? Okay,
Professor,
yeah.
can you explain again how you picked up the points? Is that a random points, or you picked up from the xt function?
No, those are random points.
Oh, okay.
Yeah.
Thank you.
Those are random points, and we want to approach fx of t. So I can't just keep picking up all these points and do it manually. It will take forever. So that's where this integral over st comes in, because s now is at this the entire two-dimensional plane. So when you do the integration, you input all possible combinations of sigma and omega, and then you watch the result.
Yeah, that makes sense.
Yeah. Does anybody else has questions? No? Okay. All right. So now that we created this fancy signal, this fancy 3D plot, what do we do with it? Let me go to the next slide here. Let's assume that this is the plot we got. That's the plot that now populates the entire S-plane. And you see three important points here. We see all this interesting surface. Well, we know the points along that surface are useless. They have no particular information. But we see that at this point, the function is tending to 0. This is in decibel scale. So a negative number means tending to 0. And these two peaks are the peaks where the function goes to infinity. What do we do with it? Well, we have here an imaginary axis. So these are the values of omega, and here we have a real axis. These are the values of sigma. S equals to sigma plus j omega. Now we want to create a function of S that will display precisely the same behavior. When S goes to this point, S is the plane here. When S goes to this point, the function goes to 0. When S goes to this point or that point, it goes to infinity. So let's create that function. Let's call that x of S. And x of S goes to 0 when we approach this point. What is this point here? What is the value of sigma and omega? You look at your copy there. We see that omega is 0 at this point, and you see that at that point sigma is negative 15. Everybody sees that? Yeah? Yeah? So what is the value of S for that point? Well, for that point, S equals to sigma negative 15 plus 0. Now we want our function of S to go to 0 when S is equal to negative 15. So if our function was, for example, S plus 15, when I put S into here, for this point, the function goes to 0. Easy, easy, easy. But that's not all, because you have two other points to account for. This point here, tell me what the values of S and omega are. Excuse me, sigma and omega. What is sigma? What is omega for that point?
Sigma is 0, omega is 10 and minus 10.
10 and minus 10, 10 and minus 10 for that one, right? That one is the same. This one here is sigma is 0, omega is minus 10. So for this guy here, S equals to negative 10j. And for this guy here, S equals to plus 10j, right? Sigma is 0 and omega is plus minus 10. Now
Isn't it the other way around?
The other way around?
I think so, right? The
Yeah.
10 in the back is, yeah.
Okay, all right, that way, yeah, good. Okay, now we want this function to go to infinity when we approach those points. So what we could do, for example, is to divide this function by S minus that, S minus 10j. So when S approaches 10j, this is 0, something divided by 0 up infinity. And we can also divide this function by S plus that, S plus minus that, so S minus 10j, S plus 10j. So when the function now reaches this point, when S is equals to negative 10j, this term goes to 0, the entire function goes to infinity. And this is the Laplace transform of that signal x of t. You see, it's a function of S now. We can expand this. It's S plus 15 over S squared plus 100, which is the same as S over S plus squared plus 100 plus 10 over S plus 100 is squared times 15 divided by 10. I just added this 10 on top here and divided by 10. You'll understand why soon. And this is another term. What is the inverse Laplace? What is x of t? If you look at the table, this is cosine of tan t, and this is sine of tan t. This is the signal x of t. Okay, that's the signal we were looking for. This was an unfortunate graph because it doesn't really match the signal we had in the beginning. This would require an exponential, but you get the idea. Are there any questions? Are there any questions? So let's just recap what we did then. Maybe in the process, some questions will come up. We use the random combinations of sigma and omega to compare a random signal with the signal we were trying to find the Laplace transform of. We did that a comparison by multiplying these two signals, taking the integration of them. This three-dimensional axis here is the result of that integration, and the 2D axis is the random values of sigma and omega. That's the graph we got as a result. Now we want to create a function of s that it would display the precise same behavior as that integration. That is, when we approach this point, which in this case is at sigma s equals to -15, the function goes to 0. So we created on top of the equation here the opposite of that, s plus 15. So when s is -15, this goes to 0, the entire function goes to 0, and we account for that point. But we also want the function to go to infinity when s approaches this point and that point. So we looked up at what these points are. This one here is s plus 10 equals to 10j. We divided the function by s minus 10j so that when s equals to plus 10j, this is 0, the function goes to infinity. And you did the same for this point, which is s equals to -10j. So we divided the function by s plus 10j. When s equals to -10j, this term is 0, the whole thing goes to infinity. And this is now the Laplace transform of the signal we wanted. Now, this is done backwards. Typically, what we do is that we take the differential equation. From the differential equation, we get here by taking the Laplace transform, and then we solve for the inverse to find the original signal. I started this from the end. I think it makes more sense to explain it that way. I started from the signal and then worked my way back to its Laplace transform. But when we solve the problems, we'll solve this in the opposite direction. We have a differential equation, and the differential equation will take us here in one step. And then we do the inverse Laplace to find the correct signal. Any questions? Oops. So why are there no questions? Let me ask that question. Because this is clear? Because this doesn't make any sense? Because you're tired? Because you're still in your beds? Is it good? Not clear? Again, if I don't hear any feedback, I'll keep going.
Yeah, I think it's clear.
It's clear? Excellent. Okay, so let's move on then. Unless someone has other questions. Okay, so this was the 3 slides that we had here. Take a look at, I have summarized this in this video. You can watch it later if you need to repeat this explanation and go through it one more time. This video was done, it has maybe a different, more information or done in a slightly different way. So maybe that one will help you grasp all the aspects of this if you need more explanation. So just take a look at it later. It's only 15 minutes long. If you need to go through this one more time. I know that this is not an easy concept to wrap your head around. It takes some time to let it sink in. Okay. All right. Now let's move on Let's go back to this. So we did the forward Laplace transform. We can also do the inverse Laplace transform. We did one step there. And the inverse Laplace transform, here is the forward. The inverse will now take us back to the time domain. So the forward take us to the frequency domain from time to S, and the inverse will now go backwards. We take the integral now over a range of frequencies, and we go back to the time domain. Okay, so just doing the opposite transformation. Now, there are a few properties in Laplace transform that are very useful for us. Here are two of them. The first one is the ability to calculate the initial and final value of any signal. What do I mean by that? Well, let's consider this circuit from last lecture. We calculated the current in the circuit through the Laplace transform. Here is the result of that operation. We have the current, initial current in the inductor times an exponential of negative RT. If you plot this function, we'll see something like this. The current starts at I0 and goes to 0 as time tends to infinity. In order to create this graph, we had to take the Laplace transform and the inverse Laplace transform, find the signal, so far, and then if you make t tend to infinity here, we can find the final value of the current. The final value would be the value of I of t when time tends to infinity. Which would be, in this case, 0. We could also ask, what is the initial value? What is this point here when the signal starts? Well, that is the limit when time tends to 0 of I of t, which turns out to be I0. This requires the temporal signal xi of t. This requires the inverse Laplace transform. Luckily, we don't need it because there are two theorems in the Laplace transform that will help us solve these problems a lot faster. The first one is the initial value theorem that says that at the initial value, the initial point when time is 0, which is what we just did there, limit of the signal when time tends to 0, is the same as the limit of the function in the Laplace domain, would be I of s in the previous example, times s, when s tends to infinity. Which means that we don't even need the inverse Laplace transform to find the final value of the system or the initial. We can just look at this theorem and we don't need the inverse step. We can also use the theorem to find the final value, and the final value is stated here. The final value of that current was when time tended to infinity of the temporal response of the current. But we could instead use the limit in the frequency domain of s times the function of interest, which was I of s, when s tends to 0. And this would give us the exact same result. The exact same result. Here is the time limit, the expression we just calculated. If you do time tending to 0 of the function, we saw there that it would tend to S0. So here it is. This is the current I of S. And I can do the same in the frequency domain by now multiplying I of s by s and finding the limit when s tends to infinity. And that turns out to be I0, precisely what we saw before. We can do the final value by taking I of s. Here it is, I of s. We multiply that by s, that's the theorem. And then now make the s tend to 0 to find the final value, or we do limit of x of t when time tends to infinity. And in both cases, we get 0. The advantage of the second option here is that that can be done without computing the inverse Laplace transform. And that will then give us the final value. We'll do examples of these with these later, but it's relatively straightforward. We just need to remember these two rules. What exactly are we doing with them? Well, we are interested maybe in where the current settles. As time tends to infinity, where does the current go? In a mass spring damper system, what would be the maximum displacement, the final displacement once a force is applied? Well, we could use one of these theorems, right, to find that without having to compute the inverse Laplace transform. Any questions here? Nope. All right, the last one that property I want to talk about today is the time shift. We know that linear systems, if you apply a time shift to them and they are time invariant, that a time shift will be reflected in the output. And this is very useful when you have signals, for example, that will trigger at given points in time and do not necessarily start at 0. For example, consider that this could be a voltage applied to that electrical circuit. The voltage goes from 0 to 5 volts at 1 second. It's held constant for 1 second and then turned off. This signal can be described by that. That's the time domain. And here is the property of time shifting in the Laplace domain. We know that if you take the Laplace transform of a function that has a shift in the time, what happens is that the result in the Laplace is the function now converted into the frequency domain times this term. This term is negative s times tau, where tau is the time shift. So for our two functions of interest, here tau is 1, here tau is 2. We have a step function, so the Laplace transform of the step function is simply 1 over s, the magnitude is 5, so you have 5 over s. That's the Laplace transform of u of t. But because it is shifted over time, then we add this additional element exponential of negative 1 times s, which accounts for the time delay of 1 second. Same goes for the other function. Is now a negative step at kicking in at 2 seconds. So the Laplace transform of 5 times a step is 5, excuse me, is missing here, 5 divided by s. But that only occurs at 2 seconds. Hence this additional element here, exponential of negative 2s, where 2 is the time shift. With that in mind, let's assume that we have this function, h of s equals to s divided by s squared plus 5 times exponential of negative 3s. What is the inverse Laplace transform of that? Well, clearly here we have two elements. The first element is this function, which is the Laplace transform of something. And then we added this term to it to say that that function is actually shifted in time by 3 seconds. By 3 seconds. What is the function? What a Laplace? What a signal gives s divided by s squared plus 5? If you go to the Laplace table of Laplace transform, you can check this later. This is cosine of square root of 5t. If you take the Laplace transform of cosine square root of 5t, we have s divided by s squared plus 5. But there is the extra term exponential of negative 3s, which means that the original signal we took the Laplace transform of was shifted in time by 3 seconds. So the actual signal must be shifted in by 3 seconds. So square root of 5 time t minus 3. Right? Because it's shifted in time by 3 seconds. And that's the original signal that originated that function. Are there any questions here? This is very important. We have a question in the assignment that we have something like this. We'll do an example later. Okay, no questions? I'll move on. All right. Last thing for today is partial fraction decomposition. Who has seen partial fraction decomposition before? Tell me in the chat if you have seen it. I suspect that most of you have seen it. Can anybody confirm that on the microphone?
Yeah, in first year calc we did.
All right. So I'm going to go through partial fraction decomposition relatively fast. The idea is that when you have a ratio of polynomials, such as this one and that, so a combination of different polynomials, we won't find that in the table of Laplace transform. We'll only find the individual terms of that polynomial. meaning that we can split, if we can now split that into partial fractions and then go to the table and solve for the inverse or forward Laplace transform of each individual element in that polynomial. That rational fraction of S. So if this function here is simply a combination of multiplication of polynomials like that, we can split it into a sum of smaller functions and then take the inverse Laplace transform of individual elements, because we're dealing with a linear system that holds, and the function can be, we can do the inverse that way. Let me, I am going to go through this relatively fast if you have seen it before. So the way we split these partial fractions depends on what you have in the denominator of them. For example, the factor in the denominator being a polynomial like that, as plus b, we'll need to create one term for that. That is c times as plus b. C is a constant that we have to determine. If we have an element like that, this will take k terms to solve for, depending on the power of k. If you have a polynomial whose roots are complex, this cannot be simplified into two real elements like that. Then you need a partial fraction with two elements on top, C1s plus C2s, and so on. Okay. And if the whole thing is squared, then we have a combination of the last two. So let's do an example here. If we have this function, how can you write the partial fraction for this? We have a polynomial divided by s plus 2 plus s times s plus 3. So clear that it falls into this category. So we need now two elements that will follow this format. We need one, let's call a constant a divided by s plus 3, plus another element b divided by s plus 2. All right, let's call this function h of s. If h of s is that function, we can find a and b. A would be h of s times s plus 3 when s equals to -3. What is the result of that? Is -2. And you can find b as h of s times s plus 2 when s equals to -2, and that gives 5. So we can rewrite this expression as h of s equals to -2s plus 3 plus 5 over s plus 2. And can finally now take the inverse Laplace. If you look at this in the table of Laplace transform, you won't find it. But if you look for -2 exponent divided by s plus 3, we know that that is -2 exponential of -3t. And 5 divided by s plus 2 is 5 exponential of -2t. And this is the signal h of t. Okay. Is this clear? Do you need more details on this, or are we all good with partial fraction? Okay. So what partial fractions do we need for this one, for this function? This one being a table of Laplace transform. So here we have two elements. We have something is squared plus 3. So if you go back to the table here, what do we have? We clearly have one element that looks like this one. So we'll take now two partial fractions, and you have another element that has complex roots. And that element will fall into the third category here. So the partial fraction for this will look like a over s plus 3. Let me just take my notes so I'm consistent with what I noted here. yeah, a over s plus 3 plus b s plus 3 squared plus cs plus d divided by s squared plus 3. Now you can now find a common denominator for this thing, that is s plus 3 squared times s squared plus 3, when we have a s plus 3 s squared plus 3 plus b s squared plus 3 plus cs plus d times s plus 3 squared. Equate this to the original function. The denominator now will cancel out. We can expand this expression. That's what we have. And once we expand this expression, here's another way to find the coefficients a, b, c, and d. We can simply create a system of 4 equations by just equating the coefficients of s squared, s to the power of 3, and so on to the other side of the equation. For example, s squared, s to the power of 3. Here we have coefficients a and c, but there is 0 s to the power of 3 on the other side. So this gives us one equation. We can equate s squared here with that equals to 1. That gives us a second equation. It's s to the powers of s and s to the power of 0 to the power of f of 0. This is all we get as a result. And now we can solve for the system of equations to find a, b, c, and d. How you exactly solve for this? You can use any tool you need. If you want to use MATLAB, if you want to use any online resources to find partial fraction decomposition for your assignments and tests, go for it. This is basic math from calculus. I'm not going to be judging how you do this. It's up to you to do it the way you prefer. Okay. All right. Are we good here? Time is at 32. Okay, let's do one exercise. And then let's do a more complicated one. So here we have the function f of s equals to 10 over s plus 1, s plus 10. And we want to find f of t. What do we do? What do we do here? Well, if you look at the table of Laplace transform, this is not going to show up there. Right, so you need to create partial fraction decomposition. You see that these are simple first order polynomials. So this can be split into a over s plus b over s plus 1 plus c over s plus 10. How do we find a, b, and c? Well, we can find a by taking f of s, multiplying that by the denominator of a, which is s, and evaluate that at the point where the denominator becomes 0. That happens when s equals to 0. F of s is that, multiplied by s, this s cancels out. And we evaluate this when s equals to 0. This is equal to 1. How do we find b? Tell me the expression for b. Is f of s times anybody?
Times s plus 1.
Times s plus 1, right? The denominator of b. What else? And we evaluate this at whatever makes
-1.
Exactly, -1, whatever makes the denominator 0. So f of s times s plus 1, what is left there is 10 over s times s plus 10. We're evaluating this as s equals to -1. This is -10 plus 9. negative 10 over 9. And C is f of s times s plus 10, evaluated at s equals to negative 10, which is 10 over s plus 1. And when s equals to negative 10, we get negative 1, negative 1, 9. Negative or positive? Positive, right? Positive. Yeah, positive. This is negative 9, this is negative 10. So it's positive 10, 10, yeah. So this writes as 1 over s minus 10 over 9, 1 over s plus 1, plus, or 1 over 9, 1s plus 10. What is the inverse Laplace transform of that? Let's call this f of t, which is the inverse Laplace transform of f of s. And that is, what is the inverse Laplace of 1 over s? Around the table, you can check that, that's 1. The inverse Laplace of 1 over s plus 1 is exponential of minus t. And that one is exponential of negative 10t. This is now the inverse Laplace of that. Now notice something interesting here. All the things that make the denominator 0 are real numbers. There is no complex point, or s here is negative 10, s here would be negative 1, s would be 0. So this function will blow to infinity only for real numbers, right? There is no omega. There's only sigma. The function only goes to infinity for real numbers. So when there is only sigma, there should only be exponential components in the time response. Aha, only exponential components, no sinusoidal components showed up, because all points here that will make the denominator 0 are real numbers. The function only goes to infinity for points where sigma is non-zero and omega is 0, leading to only exponential time responses. Any other question? Any questions here?
How come a is not equal to 0? Because f of s times s, when s is equal to 0, should be 0, correct?
Well, we have f of s, we have to multiply by s, right? So there's one s in the denominator.
Right.
And this s and that s will cancel out. So you are left with this.
I see.
They have s on top and s on bottom, they cancel out.
Okay. Okay, thanks.
Yeah. Any other questions? Okay. So if there are no more questions, let's do something more complicated. Let's do exercise number 6. This will help you with your assignment. I was doing my best to not go over time, so you have 15 minutes for it. And last time I did it, it took me about 20 minutes, so I might end up going over time again, but it will still have that in the solution, in the recorded lecture. If you have to leave, please feel free to do so when the lecture time is over. But I would like to complete that exercise. And if we don't complete it today, maybe we'll do it next week. So how are you guys feeling now? Do you want to see another lecture on Laplace transform and examples, or are we ready to move on? What do you want? What do you want to do?
I think it's pretty clear. I feel like I would like to move on.
Okay, good.
Can't speak for everyone else though.
Anybody else? You can, if you don't want to talk on the microphone, just type that on the chat. I'll take a look at it later. Anybody else has any suggestions? We can do one lecture with only examples for the inverse Laplace and whatever. Or we can just move on to the next content.
I have to do more Laplace transform.
More Laplace transform?
Yeah.
Yeah, okay. Anybody else? Okay, well, let me know in the chat if, what do you want to do? Let's do this exercise. This will help you with the assignment. So here we have a mass spring damper system. The mass is subject to a force F of t. The displacement of that mass is x of t. Now notice how the force is applied to it. The force is a step force, but that step ends at 5 seconds. Step ends at 5 seconds. So basically what you're doing is that you're applying a force to the mass, you're pulling on the mass, and after 5 seconds, we just let it go. And we want to find now the response of this system, the time response x of t for that particular input signal. Let's do that. Here we have mass is 1 kilogram, coefficient of viscous friction in damper is 2 Newton second per meter, and the spring has a stiffness constant of 10 Newton meter. Let's do that. And find here, there. So that's the system. This is the force we are applying to it. We know how to model this thing, right? I'm not going to spend much time on that model because at this point, I would expect this to be clear. So I'm just going to write the final equation. If you model this, we have f of t equals to mx double dot plus bx dot plus k. All right, this is a basic mass spring damper system. You can do the free body diagram, follow all the steps, you get to this. At this point in the game, I would expect that to be extremely clear. And if not, it's time to go back to the lecture and start revising it. How can we describe this input force? F of t is a step that starts at 1 second. So u of t starts at 1 second. Let's give this a magnitude of 1 Newton. And ends at 5. So it needs minus u of t minus 5. Are we good with this? Yeah, so this is step. This would be a step that starts at 5 and goes on to infinity. This is subtracted from the step that started at 1. So when you subtract them, this is 0. Can now take the Laplace transform of these two guys. What is the Laplace transform of f of t? Let's do the first equation here. We have f of s. F of t is f of s. Mx double dot. What is the Laplace transform of that? Second derivative of x is x of s times s squared. First derivative of x is x of s times s. This is kx, excuse me, plus k times x of s. You notice that the first derivative became s squared. The second derivative is s. This is just x becomes x of s. We can factor out x here. F of s equals to x of s ms squared plus bs plus k. What is f of t? F of t is step input is 1 over s. The step input delayed by 5 seconds is the step input exponential of minus 5s. That's the Laplace transform of this guy. Step input 1 over s. Step input delayed by 5 seconds. Transformation of the step times its inverse, its time delay. Okay. Are we good? Yeah, so now let's combine these two. We have, sorry, this is f of s. Let's combine these two. We have 1 over s times 1 minus exponential of negative 5s equals to ms squared. M is, what is the value of m1? What is the value of b2? And the value of k is 10. All times x of s.
Excuse me.
Yep.
Is the f of s equals 1s minus 1 over 5 e to next 5s? Is that from the step function?
This is, so the Laplace transform of u of t is 1 over s. The Laplace transform of a function delayed by a is 1 over s exponential of negative as.
Okay, yeah, thank you.
Yeah. Okay, so now here we are combining everything. You can now solve for x of s. X of s is 1 minus exponential of minus 5s divided by s squared plus 2s plus 10. Okay. Are we good so far? Any questions? No? Okay, now we can do the inverse. Well, the inverse is looks a bit scary because of this term here, but this term is doing nothing else than just adding a time delay. So if you know the inverse of this part with the 1, we can just replicate that with the same term, but now multiplied by this time delay that will be reflected back in the time domain. Now the challenge here is the partial fraction decomposition, because this polynomial, clearly, if you find the roots of it, will have complex roots. So you won't find that in a table of Laplace transform. Excuse me, you won't find s times that in a table of Laplace transform. This cannot be split into two polynomials with real values because the roots are complex. So this would require partial fraction decomposition, where the denominator has as plus b, or c1s plus c2, that has two terms on top, and this s will require another one. So if we expand the partial fraction of this, I'll just give you the result here. I can post the full solution now, but later, but this will require two partial fraction decomposition, one for s and one for that portion there. And if you do the partial fraction decomposition correctly, we should have this being equivalent to 1 over 10 times 1 over s minus 1 over 10 times, what did I write here? 1 over 10 times s plus 2 divided by s squared plus 2s plus 10. Okay, that is correct. Now what do we do next? Well, we need to do the inverse Laplace. The inverse Laplace of this is easy. We know what to do here. The inverse Laplace there is a bit more tricky. This is a complex, has a complex root here. We cannot split this into two small polynomials. We have to deal with it as it is. How can we find a solution to that? Let's look at the table of Laplace transform. And if you go to the table of Laplace transform, we have properties down here. Where did they go? There, where we see the same sort of denominator. We see the same sort of denominator, exponential of at sine of bt. We have a constant on top and then a polynomial in the denominator. Exponential of at cosine of bt has a polynomial in the denominator, second order polynomial, and s minus a constant in the numerator. Now, to solve for any of these guys, we need to prepare our function in that particular way. Notice here that we need the denominator in the form of s minus a squared plus b squared. S minus a squared plus b squared. How can we do that? We need this times a constant, s plus a constant is squared plus another constant. So let's think about it. Sx of s equals to 1 minus exponential minus 5s. This one, we know what to do with it. Nothing else is required. But here, we need this to be written in the form of s plus a constant is squared. Whatever constant we put in there, when you do the square, that will have to give us plus 2s. So the only way to get this to give us plus 2s is to have s plus 1 squared. Now, when you expand that, we have s squared plus 2s plus 1. But here we have plus 10. So we need to add 9. Let me repeat that. We want to write this in this form of s plus a constant squared plus another constant. Because the coefficient of s here is 2, the only way we'll get 2s when you expand the multiplication here is by having s plus 1. So we have s squared plus 2s plus 1. 2s is there, s squared is here. This gives plus 1, but here we have 10, so we need to add 9. 9 to it. Okay. And the numerator, we'll look at the functions there. We have s plus 2, but we need to create a s plus 1. So we can do this as s plus 1 plus 1. Why? Because if you look back at the table, in the cosine, we see s minus a squared in the denominator, and you see s minus a in the numerator. So that s minus plus 1 in the denominator needs to show up in the numerator as well. Well, we can use a simple trick for that. Here we have s plus 2. Now we have s plus 1 plus 1, which is exactly the same as s plus 2. Okay, so I can further expand this now in two terms. 1 minus exponential minus 5s. I'm going to go over time again, and I apologize for that, but at least we have the solution for this. Minus 1 over 10. Now the first term is this, s plus 1. S plus 1 is squared plus 9. And the other term is, don't forget that everything is multiplied by 1 over 10, is 1 over s plus 1 squared plus 9. All right, so now we are ready to do two inverses. We are ready to do this one, we're ready to do that one. This one here, though, not quite, because let's go back to the table. If you look at the table, we see that for the cosine one that required that s in plus 1 in the top, we are good. But for the other one, we have 1 divided by s plus 1 squared plus 9. And we would fall into number 19. However, number 19 needs b on top of it. Needs b on top of it. B squared here is, b squared is 9. But we need to have b on top. How do we create b on top there? Oh, just multiply this by 3. B squared is 9. B squared is 9. B is 3. So we create 3 on top. And to balance the equation, we just divide this by 3 as well. So multiply that by 1/3. Right, so 3 cancel out. But now this entire part here, let's go back to the table one more time, will fall into category, into equation number 19. We have now b squared in the denominator, and you have b in the numerator as well. Okay, now you're ready to do the inverse Laplace. Everything is ready for the inverse Laplace, but there is a little complication here. The little complication is this term. We have now 1 that multiplies this entire thing, minus e to the power of 5s that multiplies the whole thing again. So what is this doing? Well, it's simple. 1 that multiplies this, we know how to solve for. So let's solve that one first. Let's first solve that one first. So this is x of s, x of t. Now, excuse me, it's x of t. We are doing the inverse Laplace. And you're now going to take this entire part here multiplied by 1. So what is the inverse Laplace of 10s over 1 over 10 times 1 over s? That is simply 1 over 10. What is the Laplace transform of this big thing here? Is negative 1 over 10 cosine exponential of, we'll check that at the table later, exponential of negative t cosine of 3t. And this term here is negative 1 10 times 3, 1/3 divided by 30, sine exponential of negative t, sine of 3t. So this was obtained through these multiplication. Now, what do we do with the other term? Any ideas? Almost done. What do we do with the other term? Isn't it the same inverse Laplace, but now shifted in time? We are taking the same thing here, multiplied by that term that it was generated because of the time delay at 5 seconds. And this 1 times the entire thing, delayed in time by 5 seconds. So this is exactly the same expression, but now with a time shift. So we can write this as minus the same thing, but now time is delayed by 5 seconds. So time becomes time minus 5 cosine of 3t minus 5 and minus 1 over 30 exponential of minus t minus 5 sine of 3t minus 5. And this comes from that multiplication. Now, these signals only start at time 5 seconds. Here, they would start at any time. It's just that we apply the shift here. But to make them start at time 5 seconds, we need to also add the step time t minus 5. So this only kicks in at 5 seconds. Same here, times the step delayed by 5 seconds, and same there. Can you still see it? Yeah, ut minus 5. So the first part came from this multiplication. The second part is exactly the same. It's now, well, there's a negative sign here. And it only starts at 5 seconds. You see that this exponential created all these time shifts. But also, because we know that this is only starting at 5 seconds, we cannot let this part of the signal exist prior to 5 seconds. And that's why we need to multiply every single term by the step function that it starts at 5 seconds. These signals only exist, the second part only exists past 5 seconds. Okay, as specified here, as you can see from there. I can plot this and you'll see the result there. This is the signal x of t. Does that make sense? Well, it makes perfect sense. In the first part there where the signal goes up is where I'm stretching the mass. So it's going to oscillate a little bit because of inertia. And I'm holding that up to 5 seconds, and then I let it go. And then when I let it go, it simply goes back. It also oscillates a little bit before it stops there. Okay, this is not transparent. So the first part of this equation you see going up, here it is. Here it is. Right? You see going up and reaching 1 over 10 as the maximum displacement. And you hold that a portion, and when you let it go, we see the second part here kicking in that now subtracts this part from the original signal and make the whole thing go to 0.